Let us turn our attentions to the anterior pituitary hormones. So these are all hormones that are made in the anterior pituitary gland, which is really epithelial tissue, so it's true glandular tissue, and regulated because of RHs releasing hormones and inhibiting hormones from the hypothalamus. So before you watch the rest of this video, please make sure that you've watched this one that will tell you about how anterior pituitary hormone release is regulated by the hypothalamus. The first anterior pituitary hormone we'll talk about is thyroid stimulating hormone, TSH. Levels are often tested when you're looking at thyroid function, be it hypo or hyperthyroidism. So its job is to target follicular cells of the thyroid gland, and then those are stimulated not only to release, but also to make more T3 and T4, because you can't ever have zero levels. You can't bottom out of thyroid hormones. So as you're releasing that, you want to make more to restock your thyroid pantry, if you will. The next anterior pituitary hormone we'll talk about is ACTH. And again, this is one where if you look at what the words mean, the word parts mean, it will help you figure out what this hormone does. Adreno refers to the adrenal gland. Cortico refers to its cortex, its outside. And tropic means that tropic technically refers to development or an action of something being made, but in this case you can think of it as stimulating something to happen in the adrenal cortex. So that's exactly what this hormone does. It stimulates the adrenal cortex to release corticosteroids. Those are the steroid-based, lipid-based hormones that come from the adrenal cortex, such as cortisol and cortisone, aldosterone, and the androgens, which would be testosterone-like and estrogen-like, progesterone-like hormones. What triggers the release of ACTH is CRH from the hypothalamus. Those levels tend to be highest in the morning to get us ready for the day so that we can utilize the light as best as possible. Other factors that might increase the release of cortisol, especially, which is a long-term stress hormone, fever, so that you can metabolize glucose and fatty acids faster to do repair, proteins as well, do repair of the body, or stimulate the production of ATP for repair processes, low blood sugar, hypoglycemia, and stressors. Some of those stressors might be school. You know, every student's got pretty good cortisol levels. One thing you can do to decrease the levels of ACTH, CRH, and cortisol to some degree is do the Superman pose. If you look up Amy Cuddy on YouTube, she's a psychologist that has talked about the superhero pose or the Superman pose, and it really says that, you know, if you talk yourself up, and do a lot of positive self-talk, that it will help to lower some of these stress hormones, which is, you know, pretty important when you go into a test or an interview, you know, something that's really important to you. So just some food for thought. The next hormone is prolactin, sometimes known as PRL. So again, word parts mean something here. So prolactin, the pro is for, lacto refers to like lactose, milk sugars. So prolactin's job is to stimulate production of breast milk in the mammary glands of the female. In men, the role's not really well understood, but according to this article, and you can see the website up here if you want to read the full thing, this is a review of the regulatory role of prolactin in paternal behavior in males. And right here in the abstract, which is kind of the summary of this long article, The clinicians believe that by reviewing articles that were written between 2015 and 1973, that the evidence does show that elevated levels of prolactin in men were probably associated with paternal behavior that we see in human males. Interestingly and differently, whereas most hormone release is turned on by action potentials or a releasing hormone, in the case of prolactin, the normal position for prolactin release is actually off in a human body. So as we produce dopamine, prolactin inhibiting hormone, which is the same as dopamine, is what prevents us from producing prolactin. However, at the end of pregnancy, I should say, sort of toward the end of pregnancy, those increased levels of estrogen also account for breast swelling and tenderness, and that's true as well during the menstrual cycle. So now we'll look at two gonadotropins. The gonads are the testes in the male and the ovaries in the female. And again, we're looking at a tropic hormone, one that stimulates other glands to do something or other organs to do something. So here, FSH stimulates the production and maturation of the follicle. Right, so the follicle for a female is the ovum or egg. In the male, that is the sperm. Luteinizing hormone, LH, stimulates maturation of the egg as well, and the whole process of developing the egg, developing the sperm, getting the two of them together, and making sure there are appropriate hormone levels for the development of the uterus is a miraculous process. I mean, it really is, for lack of a better word, a miracle that we continue to produce more offspring, considering the number of hormones and the levels that have to be present. So this huge symphony of perfection, of parameters, has to be in line in order for us to make new people or make new squirrels if we happen to be squirrels. In males, LH also stimulates the production of more testosterone, and that testosterone is important both in the physical building of the male as well as reproductive capabilities in terms of making sperm. And lastly, we'll look at growth hormone, which does just that. It stimulates actions that are either indirectly related or directly related to the growth of body tissues. So let's look at the direct actions. The direct actions are ones that are metabolic. So they stimulate the catabolism of fats and carbohydrates so that we can use those as building blocks to make other parts of the body, or, and maybe more importantly sometimes, they are used to make ATP, body energy. So from one glucose molecule with aerobic cell respiration, we get about 36 to 38 ATPs. With the equivalent fat molecule, a single fat molecule, we get about 108 to 110 ATPs from that process. But it does take a little bit longer to make or to utilize lipids to make ATP. So that seems kind of contrary, that those would be the direct actions, but we need that energy and we need the raw materials to actually build organs like the liver or the skeleton, and then the bones as well. The bones will grow in response to growth in the muscles. So we make more cartilage, and that cartilage through endochondral ossification or intramembranous ossification, if we're talking about skull bones and clavicles, will increase the size and the density of the bones. There have been certainly news stories of athletes who've used things like growth hormone for, unfortunately, cheating purposes to increase especially muscle growth. But what that also does is it causes megaly or enlargement of other organs in an unhealthy fashion. And I think there is from everything I've read, there's sort of a misunderstanding of people that use performance enhancing drugs to say that growth hormone's not a steroid, so it can't be that bad, or it can't really be cheating because it's not a steroid. Steroids, the illegal steroids, are what people know. Unfortunately, we don't have a lot of time to talk about pathophysiology, but there's a few cases where I'd at least like to give you some exposure. So this man and this man are two examples of errors in growth hormone release and synthesis. This man right here has pituitary dwarfism. So what's happened in this case is, and it could be achondroplasia, but I'm making an assumption that it's a skeletal disorder, that he is a pituitary dwarf, which means that there wasn't enough growth hormone produced before the epiphyseal plates closed. So when those plates don't grow, the bones don't grow in length appropriately. And that will also, because of the effects of growth hormone on other organs, impact other systems as well. This man has gigantism, which means that there was excess growth hormone produced during the adolescent phase of bone growth. And what qualifies someone as a giant varies a little bit from year to year. I've heard it ranges anywhere between 6'8" and 7'2" as the minimum. And then one more disorder I'll show you, which is similar to gigantism, in that this is a case where too much growth hormone has been produced, but in this case, it's after the epiphyseal plates have closed, so the bones can't really go longer, but they do grow much thicker. And judging by the collars here and my experience in costumes, I would say that this is somewhere between the 1920s and 30s or so at the end of it. So one of the easiest things to watch, there's two. One is look at the brow here and then look at the mandible, right? The mandibular symphysis is right here, but just watch where that is in relation to the shoulder. So then it's gone down, there's a smaller distance between the shoulder and the mandible, even smaller, and then here it's actually breached the plane of the mandible. And then the other thing you can look at is the brow and how it's gotten heavier over time. There's another interesting picture that you can look for on the internet that shows the external occipital protuberance, or EOP, that's migrated about 1.5 inches or so inferiorly in someone who has acromegaly.